Hello, this is Dr. Holcomb. In this video, we'll be talking about the E1 mechanism and the formation of alkenes. We'll begin our discussion with the acid-catalyzed dehydration of alcohols. In this reaction, a tertiary alcohol is treated with sulfuric acid and heat, forming an alkene and water. This reaction is similar to the SN1 reaction of alcohols with hydrochloric, hydrobromic, or hydroiodic acid. In both cases, the reactions are promoted by acids. The relative rate is tertiary greater than secondary, much greater than primary, and the rate law is unimolecular. This suggests that the reaction proceeds by way of a carbocation. As with the SN1 mechanism, the first step is protonation of the alcohol. This step is fast and reversible. The breaking of the carbon-oxygen bond is the slow, rate-determining step. The result is the formation of a tertiary carbocation and water. Water can be removed to drive the equilibrium according to Le Chatelier's principle. Removal of an adjacent proton generates the product alkene as well as hydronium ion. Hydronium ion, which is the acid source, is therefore a catalyst. Let's take a closer look at the elimination step. The carbocation carbon is defined as the alpha carbon, and adjacent carbons are defined as beta carbons. The hydrogen that's abstracted is then a beta hydrogen. The alkene that's formed is classified as disubstituted on the basis of the two alkyl groups. It should be noted that this step is an equilibrium, and alkenes themselves can be hydrated. The consequence of this equilibrium is that thermodynamic product mixtures result. The relative rate of alcohol dehydration is dependent upon the carbocation stability. Consequently, tertiary alcohols react faster than secondary alcohols, which react much faster than primary alcohols. In cases where there are multiple beta hydrogens, product mixtures are formed. When we examine the starting material, we see that there are three different groups of beta hydrogens. The major product results from the removal of a proton from the carbon bearing the fewest beta protons. This observation is known as Zaitsev's rule. Again, Zaitsev's rule is that the major alkene product arises from the loss of a proton from the carbon bearing the fewest protons. Zaitsev's rule is a consequence of alkene product stability. Experimental heats of combustion of a set of isomeric alkenes indicates that the disubstituted alkene is more stable than the monosubstituted alkene. Similarly, the trans disubstituted alkene is more stable than the cis disubstituted alkene. The increase in the energy of the cis alkene is due to steric interactions of the two methyl groups. The bottom line here is that all else being equal, the more highly substituted alkene is more stable than the less substituted alkene. So if the option is available, tetrasubstituted alkenes are formed more rapidly than trisubstituted, which are in turn formed more rapidly than disubstituted trans, formed more rapidly than disubstituted cis, which are more stable than monosubstituted alkenes. Product distributions are a consequence, then, of alkene stability. So Zaitsev's rule is a useful shortcut to determine the product distribution of alkene formation. It states that the proton that will be removed is the proton on the carbon bearing the fewest protons. Removal of this proton gives the tetrasubstituted alkene as the major product, and the disubstituted alkene as the minor product. Now it's your turn. Pause the video and determine the products, both major and minor, that are formed given these reaction conditions. Here are the products, with the major first and the minor second. But there's something curious about this minor product. Let's take a closer look at the mechanism for this reaction. The first step is protonation of the alcohol to form the oxonium ion. In the rate-determining step, the carbon-oxygen bond breaks and a secondary carbocation is formed. We can identify the beta hydrogen, which is attached to the beta carbon, and a more distal gamma hydrogen attached to a gamma carbon. Only the beta hydrogen can be abstracted to quench the carbocation. The gamma hydrogen is too distant. So what's going on? In this case, hydride migration gives rise to a more stable tertiary carbocation. So the major product is governed by the removal of the beta proton to give the more highly substituted alkene. The minor product arises from the more stable tertiary carbocation and the removal of the new beta proton to give rise to a disubstituted alkene. Because these are equilibrium steps, the product distribution is governed by product thermodynamics, and the major product is the trisubstituted alkene, despite the fact that the tertiary carbocation is more stable than the secondary carbocation. Again, the ultimate product distribution is governed by thermodynamics, and the trisubstituted alkene is more stable than the disubstituted alkene. Now it's your turn. Draw the mechanism that rationalizes the formation of the following products. Pause the video now. In the first case, an alkyl migration leads to ring expansion and the formation of tertiary carbocation. Removal of the beta hydrogen from the carbon bearing the fewest beta hydrogens gives rise to the more highly substituted alkene. In the second case, migration of a methyl group gives rise to a tertiary alkene. Removal of the beta proton gives rise to the alkene. Notice that the other beta proton would give rise to an alkene that's overly strained. In the third case, migration of a methyl group gives rise to a tertiary carbocation, which upon deprotonation gives rise to the tetrasubstituted alkene. The formation of the cyclopentane product can be rationalized by a ring contraction, which forms a tertiary carbocation and subsequently the tetrasubstituted alkene. Alkyl halides, under the right conditions, can also react to give alkenes. In this case, a secondary alkyl bromide is subjected to heat in methanol and gives rise to the trisubstituted alkene. The combination of a secondary or tertiary alkyl halide and a poor nucleophile like methanol as solvent and heat are conditions that are favorable for elimination reactions. Recall that subjecting a secondary alkyl halide to a good nucleophile in polar aprotic solvents affords the substitution product. The different outcomes of these two processes then results from the nucleophile, the solvent, and the presence of heat. Typically, in the reaction of a secondary alkyl halide, a mixture of products are formed. For this reaction, we have the SN1 substitution product and the E1 alkene. The product distribution tends to be a function of temperature. Higher temperatures result in more elimination product. This can be rationalized according to the equation for Gibbs free energy, in which delta G negative is a spontaneous reaction. The elimination reaction leads to an increase in entropy, delta S. The increasing entropy of elimination is amplified by increasing temperature, leading to a more negative delta G and a more spontaneous process. Of course, because we're actually considering rates of reaction, we must consider the transition states and the delta G of activation. But the outcome is the same. Increasing heat increases the percentage of elimination products. So when we analyze the reaction of a secondary or tertiary alcohol, we have to consider the solvent, the nucleophile, and whether or not heat is applied. In this case, the solvent, water, is a poor nucleophile and heat is indicated. We can therefore expect a mixture of products arising from E1 elimination and SN1 substitution. Because of the heat, we expect that the trans and cis alkenes are the major and minor products respectively. Substitution products are also formed as a racemic mixture. All of the products can be rationalized as arising from the secondary trigonal planar carbocation. Now it's your turn to apply this reasoning to the following set of problems. Consider the substrate, the solvent, the nucleophile, and the temperature to determine the major product. Here are the major products that would most likely arise given the conditions. How did you do? The lesson here is that heat can promote E1 elimination for secondary and tertiary alkyl halides. But don't forget, you also have to take into account the nucleophilicity of the nucleophile as well as the solvent and whether or not the solvent can attenuate the nucleophilicity of the nucleophile. For any reaction, you should assume that a number of products are formed, but the major product is determined from this multidimensional analysis.